Okay, so I think we'll begin this session now. So it's a great pleasure to welcome Gregor Weihs, who is a very old friend, as well as, So now the introduction will be about his professional achievements. So he's the head of the Institute for Experimental Physics, University of Innsbruck, and formerly an associate professor at the Institute for Quantum Computing, University of Waterloo, now an associate faculty there. And more importantly, he's the vice president of the Austrian Science Foundation and kind of governs the funding there and so on. So very important position that, a non-academic one. So welcome, Gregor, and the first lecture is on quantum communication and entanglement.
Thank you very much, Rishi. In fact, yeah, the title is quite generic, and we'll see wherever we get. It's also going to be extremely basic, at least for a start. So if it's really too basic, just let me know. In fact, so I had planned on. It says that there will be 2 lectures and 1 tutorial. Tutorial, I guess we'll do differently, very differently. I have a few things, and you might decide on what you wanted to do. This is also a little based on some course I give on sort of photonics and quantum photonics, if you will. And in fact, it's also a bit geared toward people who are on the theory side, but might want to learn about actually doing experiments. Okay, so it has a lot about optical components and so on. All right, and maybe just for a little bit of motivation. So this is going to be about light. I mean, we heard about light already earlier. This time it's going to be very, very straightforward light, the light you can see, and you know that in a lot of quantum information, in fact, started with optical experiments. We've been using optics to do various things that are part of what we call, I guess, quantum communication, where we would have QKD. This is in fact a picture of our experiment in Waterloo, or teleportation, which was done first in Innsbruck, quantum teleportation. And the techniques that I'm going to talk about and the sources that I'm going to talk about can also be used for, I guess, extending the range of quantum communication channels via quantum repeaters, which were also invented in Innsbruck, by the way, by Hans Briegel. And they use the idea of entanglement swapping, which we can also use to generate higher entangled states, which in turn we could use for doing foundational experiments, which I guess if my thesis advisor was Anton Zeilinger, and so his primary motivation for doing all this was this hope of getting a deeper understanding of quantum mechanics. I don't think he ever really wanted to build devices. Maybe nowadays he does, but it was about sort of unlocking the mysteries, which are mostly in the interpretation and not in the actual formalism or in doing experiments. And so you could criticize that all of these experiments, we always know what comes out, and still one has to do them. All right. Of course, I looked for something about light in India and learned that one of the most important festivals is the Festival of Lights, Diwali. And so the light that we're going to use is not any different, really, just usually a lot fainter so that we can hardly see it. And the other thing that's important is that it's actually interesting. For a long time, I've been wondering, why, where would you do an experiment? This morning we heard, we're using this laser, which is 532 nanometers, like the green laser here, but there's really no reason for it. It's just a very common laser wavelength. But in fact, if you look at the spectrum, there are some reasons why you'd want to do things one way or the other. You could say, well, it'd be great if we used light at the very long wavelength or slow oscillating end of the spectrum, because there we could actually have a probe that measures the field over time, like with an oscilloscope, and we wouldn't have to deal with interference experiments. We could really just measure the amplitude. On the other hand, these waves, I mean, first of all, your experiments would be very slow because things wouldn't happen very frequently in time. And on the other hand, it's also difficult to have these waves propagate for a long time. They usually meet some obstacle at some point. On the other hand, at the extreme short wave end, we hardly have any method to manipulate this radiation. You know, gamma rays penetrate through everything. They're dangerous too for you. And so in the end, it happens that we can see visible light, and it turns out to be a very convenient range. There is nowadays we have detectors that are very efficient. For a long time, it was actually tricky to detect single photons in the visible range, and it still is difficult in the infrared range. But we can do that now with very high efficiency. We have materials spanning very large ranges of refractive indices. Making structures on the order of the wavelength is also an issue, but we can do that nowadays. We couldn't some years ago. And so in the end, it's convenient that we can actually see this light that we're working with. However, as we'll learn in a bit, if we want to communicate over some distance, we actually need to go, I mean, on this graph here, it's really almost the same point, but we need to go a bit into the infrared. Oh yeah, and then, one thing I forgot. If you wanted to do experiments at very low frequencies, of course, you'd also have to work very cold because all your noise the noise would be very strong. But nowadays, people can do these experiments in superconducting circuits and waveguides on superconducting circuits, which are very cold, and they can count single photons at those frequencies of a few gigahertz as well. All right, so if we talk about optics, I guess the most classical one, or the simplest one, is geometric optics. And then I think you heard a lot from Robushi about physical optics yesterday, where we have to do with diffraction and other phenomena where light interacts with matter. And then one way of saying where is the quantum regime is if this is the regime where the wavelength is much smaller than the objects, and this is the regime where the wavelength is about at the size of the objects, then quantum optics is the regime where the wavelength is much smaller than the object. No, sorry, the other way around, where the object is much smaller than the wavelength. So where light interacts with a single atom, but that's not a proper definition. That's just some way of remembering. All right, so here's the plan, and please, if you have any questions, just shout them out. We'll just go however far we get in the 2 lectures, and whatever we miss, we miss. So I was going to talk a bit about what I mean when I talk about the photons. So you'll see sort of an experimentalist interpretation of field quantization, and then about how we might go about encoding information, quantum information, onto a photon. I call this optical qubits. They don't have to be qubits. They could be higher dimensional systems too, so qubits. And then I'll talk a bit about the components. So the things that we actually use in the lab to manipulate states, to manipulate light. And then, and this is my main research topic these days, is how do I make special states of light? How do I make quantum states of light? How do I make single photons? How do I make pairs of photons? So you can specialize in many things. You can't do everything. And sources is what I do. Other people work on detectors. And so there, in terms of sources, we're going to talk about what we call spontaneous parametric downconversion. And then I'll show you how we do this in semiconductor waveguides nowadays. And another area that I work on is quantum dots, so very small semiconductor regions that are single quantum emitters of light, and we can make single photons. We can also make entangled photon pairs. And recently we've even made triplets, not entangled yet, but we'll see how that goes. All right, so very, very short quantum optics reminder. So this is part of quantum electrodynamics, except that we always, in our case, in quantum electrodynamics, matter is always in a very low energy state. So we don't actually have to calculate, I don't know, higher order Feynman diagrams. These are always very elementary processes. You know, I gave this for some time ago. This was really meant for computer scientists, you know, who know very elementary physics, but no quantum physics, or not much. And it turns out that they know even less, right? They don't know what a harmonic oscillator is, and so it becomes really difficult. All right. But thinking back to your quantum mechanics, you know, you might have seen. I hope you would have seen field quantization before, because I'm not going to really explain it to you. But there's a few things that matter here. And that is, if you think of the position and the velocity or momentum of a charge, then you know that they're complementary quantities. You can't there's an uncertainty relation between the momentum and the position. And so for a particle in a field, same will be true for the electric and magnetic field components. And so in a way, these should also be quantized, but there's, I guess, no, I mean, you can of course give a prescription, but you should also have a motivation for why you want these fields to be quantized. And so in that sense, because they're complementary, we will try that, and the usual way of doing this is to you know, think of a box and look at waves in this box, and then every one of these waves, every one of these modes will be a harmonic oscillator, and we can formally show that on just the next slide. And then once we recognize that these are harmonic oscillators, then they will obey some commutation rules if we consider them quantum mechanically, and eventually we will find that our photons are the elementary excitations, the energy eigenstates, if you will, of these harmonic oscillator modes. And importantly, there will be a 0-point energy, which for my, for what I do is really usually not so important. All right, so here's, and this is the super fast way of doing it. Here are our electric and magnetic fields expressed in terms of complex amplitudes of the vector potential. And this is all in harmonic waves. So in the box that we put, and then here's our energy density, the electric field squared and the magnetic field squared. And you see this is all done in a non-covariant form because we never have fast-moving stuff. And in the end, we have we can have a p and a q coordinate, which is pretty much something like the electromagnetic field, and so our field modes in terms of the vector potential look like harmonic oscillator modes. And in this way, we can just use the quantum mechanics of the classical mechanical harmonic oscillator, where we have a coordinate and a momentum, and here in a normalized version, and then we can define our ladder operators for creation and annihilation operators, find their commutation relations, and then rewrite the Hamiltonian in terms of these two operators. And again, we have the 0-point energy of our harmonic oscillator. So now let's look at some properties and some states. We have the energy. The energy will just be the frequency of the mode times the number of quanta in our harmonic oscillator, and the number operated is just the A dagger A. A dagger are non-Hermitian, and they actually take us from one eigenstate to the next one. So if these are photons, then this is creating a photon, this is annihilating a photon, and so an n photon state would be written by applying the creation operator n times to the vacuum. This is our vacuum state. All right. And then sometimes I see this microphone thing is a bit trickier. To look this way. The thing about what's a photon? What's a single photon? So it's easy to write down the Fock state in a single mode. All right, but that's never what we really have. At least, well, some people have super duper cavities that have very, very clean modes, and they might have something close to a Fock state in that cavity. But even the best cavity that we can make, even our sort of the experimentalist version of the box that we wrote down, always has a finite line width. So what is it that you really have? You have to build superpositions of these modes, obviously, but because they're all solutions to the same problem, to the same Hamiltonian, we can build any superposition we want. And in the end, what Anton Zeilinger would say, a photon is a click in a detector. But it's a very different notion of a photon from, if I say a single photon is really a Fock state in a given mode. In the end, we have photodetection theory that tells us how to model the response of a photodetector, which really responds to the electric field. And I've written down the electric field again here, and this is just in this mode K. So for a certain wave vector with a certain polarization, which isn't even mentioned here, it's actually in the vector of the U function here. And so what this photon really is a bit of a tricky thing, right? If it's in a proper cavity, it actually fills the entire mode volume of the cavity, so it's not in a certain point. But as experimentalists that operate with sort of beams that propagate, we usually like to think of moving photons. So we would really have to build running wave superpositions of our originally quantized versions. Which wouldn't be a problem, but you have to believe in sometimes you have to believe so if an atom emits a photon, right, then the energy or the state of the atom becomes entangled with the mode that goes out. So unless you believe in some kind of continuum, this entanglement will persist maybe for a long time. And so only when the detector actually clicks, you reduce this entangled state to a product state, or disentangle the atom. All right. So this was just a quick thing. Yes. Right. Yes. I mean, usually when we calculate spontaneous emission, we actually assume that it goes into sort of infinite space, right? But that's not necessarily true. In fact, if you look at what the atom does inside a cavity, you will see that the excitation can oscillate back and forth between the atom and the cavity, right? So there you really have it, you really can't speak of the two as separate things. So the eigenstates would really be superposition states of the atomic wave function and the photon wave function. Pardon me? I didn't get the first part. Yes, I guess I mean, of course you could go further, and that's actually an interesting discussion, because what's the detector? It's again a collection of atoms or matter that absorbs the light, right? So at some point, that's what I said. This is really a way of clarifying very fundamental questions, because what that would mean is that a detector gets entangled with the photon, which was entangled with the atom in the first place. So now we have an even larger entangled system, very much in the idea of the von Neumann chain, where one thing after the other, now me and now my friend, or gets entangled with this system, and then where does the cut occur? I have no idea. Yes. So in a photon that comes out of the laser will usually be in a mixed state, right? Because it. Mm-hmm. That's right. Yeah. Well, I would think so. If you believe that the detector actually reduces the state at its end, right, by some kind of process that we can't describe. But usually in a detector, there's some strong nonlinearity involved that makes sure that you know, in the detector many modes get entangled with the previous one, and so effectively one traces out this environment, which is really the large detector or so. But difficult question. In fact, also relates to this here. So one of the frequently used states in quantum optics are so-called coherent states, which are eigenstates of the annihilation operator, and we write them with an alpha inside, and they are in some way they're just a rather simple superposition of many different Fock states, number states, in a way so that they have what we call a Poissonian, a Poissonian distribution of photon numbers in them, and I'll have some pictures of that in just a bit. And these were constructed really so that one could sort of, for very large alphas, approximate a classical wave. Because there's also the question of how do we describe a sort of classical light beam approximately by quantum means, and that is nice that it works out that way, that if we have very large n's or very large alphas here, so large expectation values in this case of the mean photon or large mean photon numbers, we get like it's shown here out of Lauden's books, we get an electric field that oscillates like a sine wave, so very much like we would expect it. And when alpha gets smaller and smaller, then really this means we still have a sine, but it's kind of noisy. You know, we can't at any point we can't say exactly what is the phase, where does this cross the zero. We don't know how high is it. We also don't know exactly. So there's an uncertainty associated with both, which directly comes out of the complementarity of P and Q, or whatever you call these quadratures, and then the state is very often used to describe what comes out of the laser, and but that has been criticized too, because this state, even though it has a superposition of many photon numbers, is still a pure state. So this would mean it cannot be entangled to what happened inside the laser. So really, what to give a proper description of a laser, which has is a cavity with a leaky mirror on one end, would have to be a mixture of all these photon numbers with the proper Poissonian photon distribution, which usually works. Or another way, you could have a phase randomized coherent state, and it would give you the same thing. All right. So then let's look at light sources. And in fact, so what I have here, I would all call classical light sources. So lasers, even though they sort of were invented a lot later than quantum physics, about 30 years later, I would say, or more actually, 35, are still classical in a way. Classical in the sense that they output states that have very classically looking photon distributions. In fact, here's again sort of this is the idea of the first laser that was made, the ruby laser, which contains a ruby crystal, and energy gets put into this ruby crystal from a flash lamp, and this excites the ruby atoms to. In fact, this level scheme doesn't really apply to the ruby laser. So it's stupid to put it on the same page, but puts the ruby atoms in an excited state which is kind of longer lived. And then if you have enough population in this upper state, then any field inside the cavity will create stimulated emission, and so bring the atoms back down. And in an actual laser, in order to maintain some kind of output. We would have, here is this pump, which would be the flash lamp in the case above. And then it's important to maintain this inversion so that we have sort of a higher number of atoms in an upper state than in a lower state, in which case there can be more photons emitted than absorbed in the laser mode. And what happens then is that above the threshold, so there will be a threshold which is determined by the losses, mostly of the round trip losses of the laser light propagating back and forth between the mirrors, and the gain, which comes from the stimulated emission. So there will be a threshold, and above that threshold, we will observe this Poissonian photon distribution at the output of the laser. Below the threshold, it'll be thermal distribution. So I was just wondering, I had a picture of the actually next page. Here's a plot of Poissonian versus thermal. Thermal is basically, I haven't written that down. It's basically, you see that the green one is always the thermal one, basically a geometric series. So the probability to have 2 photons is the square of having 1 photon, and so on. Basically a geometric series. Poissonian, of course, is different. Poissonian, for very small means, looks almost like thermal. There's hardly any difference. But then as soon as the mean gets larger, the Poissonian has a peak somewhere. And of course, for very large numbers, as you know, Poissonian really evolves into a Gaussian. But it still has this property that the spread of the Poissonian is equal to the mean, or the root of the mean, I should say. Variance is equal to the mean. All right? And if we now look at these photon streams in time, we find that Poisson distributed photons, just like in radioactive decay, come out randomly. Randomly meaning that if I fix a given time interval and keep counting photons for the same time interval, I will find an average value, and then I will find that the variance is the same as the average value. Okay? In fact, if I looked at the time intervals, does anyone know what do I find for the intervals between the photons? If I did a distribution of the time intervals for a Poissonian source. It's the same if you drive across a field or a road with lots of potholes that are uniformly distributed. You look at them from the top, and you count the time between 2 potholes. The same distribution. Anyone have an idea? I mean, it has to be something that decays, right? Because if you wait long enough, there has to be at least the next one. So it's something that's 0 at infinity. And it's, yes. Any ideas? It's a very simple answer. That's right. So the probability density per time interval is constant, precisely. But I am asking a different thing. I'm asking what's the waiting time? So for the next event. No, it can't, because Poissonian distribution is a discrete distribution for a number of events. Where now I'm asking actually for a continuous distribution, because the time intervals are sort of continuous. It's exponential, precisely. Very good. Yeah, it's exponential. So it's something that's good to remember. Happens, you encounter this frequently in life. Exponential distributions of waiting times. And now it turns out, if we look at the thermal source, it's actually worse. It's not exponential, it's sort of super exponential. It decays faster. Meaning also that it has a higher mass, as the mathematicians would say, or higher density at short times. So thermal photons actually come in bunches. And the reason for that is stimulated emission. And now you'll say, this is crazy talk. So you just told me that the laser operates on stimulated emission. Why is it then that thermal light has this bunching, which is caused by stimulated emission? And it's really that the laser does not operate only on stimulated emission, it also operates on feedback and on a fixed pump. It operates in some kind of energy balance. And if there's more photons, they will also be absorbed. So the dynamics of the laser sort of fixes the photon number output at this Poissonian, and actually suppresses these thermal fluctuations that occur when an emitter emits into a certain mode, and if it already finds a photon there, then a second photon is more likely to come out, which really causes these bunches here in the thermal source. All right. I mean, both of these are, for experiments. If you do diffraction experiments like Ugushi and I do, you don't really care how the photons come. In many other cases, you might care. So you'd want sources that are actually better than that. Please. Very good question. This relates to what, in what am I observing my photons? If they are, in fact, as I said before, photon in a cavity is actually, it's all the time and everywhere, right? There's no dynamics. So now if I look at this here, in real life, what I have to look at is a certain coherence time, or coherence volume, if you will. So when I talk about stimulated emission, then it would really be a second photon within the coherence time. And the coherence time itself, of course, has to do with this wave packet that I'm building. If the laser outputs or the source outputs a certain spectrum of light, then I can, related to that spectrum, define a coherence time, and which would be sort of the Fourier transform of the distribution. And then I could say, so simultaneity in that sense is defined with that time, or also in spectrum, it would have to be in the same spectrum. So if the source is fluctuating in its line, then I would have to average over that. Yes. Very good question. In most cases, unfortunately, the answer is rather boring. Detectors are usually rather broadband, so they don't actually pick out certain frequencies. And also the time resolution is poor. So the detector in that sense, in most cases, is not Fourier limited, which means that the detector, in fact, averages over all of the stuff that comes out. And so it does a time integration. Yes, precisely. And then you could, in fact, stretch your photon. If you filter it narrowly, you actually stretch the photon. Or you stretch the part that goes through, right? Whatever gets reflected has a different shape too. Yeah, you can do that. And in fact, there's a nice device, which I'm not going to talk about. It's called a streak camera, which uses a sort of a very fast deflecting electron beam to time very precisely. You can get a time resolution of down to about 500 femtoseconds. So you can sort of image photons in time. And if now also you disperse them with the grating onto that camera in the one axis and you have time on the other axis, you can actually see the Fourier area. And you really see that if you increase the spectral resolution, you ruin the time resolution. So you can actually see this effect there. Except that the detector itself is still extremely slow and just integrates over these screens. All right. So for many experiments, this is what we would want, And again, there's a contradiction here because I say single photons and then I show you many. All right. So every little bar here is supposed to represent a photon. So usually when we talk about single photons, we mean something that a source that gives us maybe at regular time intervals, gives us a photon out with a as good as we can efficiency. But maybe one of the minimal criteria that we would apply is that two photons never come together. There's some kind of minimum time between two photons, and if these small time intervals are less likely, then we also call the source anti-bunched, but we'll look at this in a bit more detail. So, if we looked at single photon sources, so if the minimal criterion is that the probability to have n more than 1 photons, to have n bigger than 1, should be much smaller than the probability to have 1 photon. So that's a sort of a minimal experimentalist criterion for when you're allowed to talk about a single photon source. Another thing that we could want, though, is that P1 is much bigger than P0, and that, in fact, has not been true for most of the single photon sources that have been demonstrated today. And that has to do with the fact that if you want a single quantum emitter that you pick the photons up from, it's usually very small, and it's difficult to collect from a small emitter because it radiates into all directions. And then we'll talk about this in just a bit. All right, and maybe just already at this point, what are the candidates to have single photons, candidate sources? One of them I'm going to talk about are quantum dots. So these are small semiconductor regions. There's also so-called color centers. You've probably heard of the nitrogen vacancy center in a diamond, which is one example. There's many color centers, and not many of them have been explored. In fact, the latest fad is the silicon vacancy center. I don't know if you've heard about that. Seems to be even better than the nitrogen vacancy center, at least for as a single photon source, because it turns out whatever you do, you'll have to make some effort. So a single atom you have to trap somehow in vacuum, an ion or an atom. Single molecules also need to be isolated in some kind of matrix. Whenever you have a matrix, like in these first 3 cases, dots, color centers, molecules, you will have to work at low temperature because the matrix, as we know from the movie, interacts with the emitters, and you really have to work at low temperatures to reduce the coupling to the environment via phonons. All right, so this is one thing. And what is the standard way of measuring your performance of a single photon source? The so-called Hanbury, Brown, and Twiss experiment, which I hope you've heard about before. And this is their original version. What did they do? They had an arc lamp and then 2 photomultiplier tubes. They were trying to see how the fluctuations in the photocurrent of one photomultiplier were correlated or uncorrelated with the other one. So they did not actually count photons, by the way. It's also a misconception. Nowadays, we call this Hanbury-Brown-Twiss experiment, where we count photons and do coincidence detection. This was really continuous currents coming out of these PMT tubes. So in this case, what's being measured, I claim here, I don't prove, is something like an average of the product of the intensities or the powers, in this case, of the 2 detectors. All right. And then what they did, actually, they moved the one. So they actually measured the correlation of the photocurrent of 1 point R1 times the photocurrent of R2, and then averaged, in this case, over time. Now, in most cases, what we would want is we would want to average over our state psi. And in most experiments, this basically is translated into an average over time by some kind of assumption of ergodicity, so that the state, if the state sort of, or every implementation of the source does the same thing, then this is how we sort of equate the state average with the time average. And in this case here, it was just the same way. And then, so in other cases, we might be interested in doing T1 times intensity at T2. And then often we write this for a stationary source as T and the T plus tau. Because for a stationary source, it wouldn't matter whether I do it earlier or later. It really just matters that I take a certain time difference. Yes? That's a good question. I don't actually know. But I think it has to do with, I don't know how this correlator here works. Basically taking the two photocurrents, some kind of multiplication, and then integrating motor might be, does anyone know? Have you looked this up before, Rishi? No? I think I did one once, but it's so long ago that I don't know, I don't remember anymore. But I'll look it up before the next class. I think, so this does the multiplication of the currents, which is usually done by amplifiers, right? And then, yeah, how do you integrate? But how does a motor integrate? I don't know. Yeah. Device. Yeah. It's a good question. I'll look that up. Okay, so in that sense, in terms of our wish list, now if we looked at, so if we now normalize this by dividing by I of t and I of t plus tau, which should be the same for a stationary source, so it's really just I squared here, then for a source that has no correlations between earlier and later, we would expect this to be completely flat, right? Which is also what we expect, or what we can calculate if we take a coherent state and plug it in here. And of course, the intensity is just the basically the square of E, or of the electric field. Then we find that we really get a flat line equal to 1. So this is a in fact, of course, it's called the second order degree of coherence. Actually says that here. It's not a correlation function in a statistical sense. Those correlation functions should always be between -1 and +1. So in that sense, it's not a statistical correlation function, but it's very often called correlation function. And then, as we said before, thermal light has sort of prefers sort of short time intervals. So that's why it shows a peak here at 0. At very long times, the power here and power there if it's stationary, then this should always give 1, right? Because there shouldn't be any correlation between these at very long times. All right, and if somehow we arranged for our light to have a preference for, or to have no preference for small time intervals, then we would call it anti-bunched. So here this second order degree of coherence would ideally be 0 at 0, and then also go back towards 1. And in fact, I don't know if I have that here, but very often you will find an identification between. So I have anti-bunched and bunched. And there's two more things, something called sub-Poissonian and super-Poissonian. Now, anti-bunched and bunched, I've explained here. Sub-Poissonian would mean that in a fixed time interval, the fluctuation would be smaller than for Poissonian source. So the variance would be smaller than the mean. Whereas super-Poissonian would mean that the fluctuation is larger, or the variance would be larger than the mean. And usually, an anti-bunched source will be sub-Poissonian, and usually a bunched source will be super-Poissonian. but this is in neither direction a logical equivalence. Okay, I could have an anti-bunched source that is super Poissonian. In fact, I don't know if anyone can see this here really. I could draw some G2 curves here now for, if this is T, for example, something that looks like this. We would call this anti-bunched because small time intervals are less frequent than larger time intervals. But it might also be, we can't see this from here, of course. It will probably also be super Poissonian because it seems to have large fluctuations. It seems to have some kind of structure to it. Whereas I could have, so this would be this case here. And there could also be a case where I have something that is bunched, but still sub-Poissonian if it's, I don't know, maybe like this. So this again is the G2. Right? This is bunched because at zero time, it's most likely. Yes. Exactly. Except that, I mean, by definition in quantum optics, we would only make these assignments of bunched or anti-bunched for the, not for the actual measured quantity or measured, but for the actual, I mean, whatever it should be in theory. Now, of course, for some we might not know, because as you point out correctly, if I have a slow detector, then it will average over here, so I will really see something like this, maybe, or not see a dip at all at the center. In fact, this is what, if you look at the data, which I don't have here, for this paper, I don't know if you ever did. I think it doesn't make a difference actually, in the sense that how do we measure this with photons, right? What is the equivalent? We do the same experiment, but now we have detectors that give clicks. So we always find some kind of time difference, and then we would just plot, you know, for every count we would plot a line here, and then we would collect this. So the time variable is still continuous. Right? But we don't actually take the product ever. What we plot, and this is another thing. What we usually plot is we plot the distribution of time intervals between detector and between one photon and the next. And I haven't shown that that is the same thing as this at all. And in fact, it doesn't. It's not always. It's only in a very special cases it close. Only in the case where you have very, very low, very, very small photon number, then this distribution that we usually plot. In fact, I have pictures here. So this is what people actually do. What people actually show you as a graph. But what have they really done in these measurements? I'll do this on the board. So again, they take the source, and then they put the beam splitter, they put one detector, another detector, and in the simplest case, they record the time. So I'll call this T1, and I'll call this T2. You just measure the time against the clock. And then they will give you a diagram which basically plots T2 minus T1, and you will get, you'll get a lot of entries here. Also, this is not normalized, so you'll get, I don't know, and then you would plot the relative frequency, of course, with a certain binning, which is, I think, what you meant, right? Somehow, so I have to put some binning here. I basically plot the histogram of these time differences. And it is true that in the case where the probability that two photons come very close to an individual detector is very small, in that case, this will approach my G2. Yeah? Yes? I think that's a statistical question, right? If you have enough data in your small bin, you can make your bin arbitrarily small, and if you have enough data. So there's two things here. The detector itself might not be accurate, right? So the time it gives you, it will give you some time in your measurement against the clock, but it may not be accurate in that. So it'll smear out whatever G2 function you're hoping to see. And in that sense, it already makes a decision about what kind of time to give you. But that's an averaging effect, right? So here I would just take the state, and in my averaging here, I would take, let me see, if I take this, right? I would have to put an extra integral over a certain over a certain interval, I don't know, 0 to, I don't know, 1 nanosecond or so, that basically smears out this response function. So that the detector will do. And then your time measurement system might add something to that itself. So in that sense, you're right. In some cases, I don't have a choice. I wouldn't even know whether two photons were simultaneous or not. But usually, if there's any sharp features in the distribution, they could only get smoother, right? It wouldn't produce sort of an artificial anti-bunching. Like if your purpose was to prove that you have a single photon source or an anti-bunched source, then a bad detector wouldn't give you a false positive. Yeah? Yeah, maybe. False bunching. Yeah. Yeah. Yeah, maybe. Okay. All right. So these are plots that people could show you, and you actually see here that it's not normalized. So this is really just the histogram of counts or a plot of the time differences between these two detectors, and it's rather easy to show that these are proportional to this G2. And then another thing you might see is a diagram where you have lots of spikes, and this is if you have a source that is not completely stationary, but that emits a train of single photons, so it's sort of stationary in that it emits the same thing but periodically. I don't know. All right. And then we already talked a little bit about coherence. That's another thing we could actually discuss in the tutorial. Coherence is a much used word, and very often people don't actually know what it means, I found. And coherence, experimentally speaking, is what I find in an interferometer. Okay, so I have an input here, and this is what I call a pseudo Michelson interferometer, because it looks like a Michelson interferometer, but it's actually a Mach-Zehnder interferometer. with a short arm, or with two arms where one arm can be extended, like a trombone. And now if I have light coming in here, then one photon, now we're only talking about one photon, could go either way, either this way or the other way, and depending on how much I've extended it here, I will interfere the same, in the photon language, I will interfere the same photon with itself. And then depending on whether I see fringes here, so I vary the phase, I vary the length, and I vary the phase, and I would see the photon go to either output or to both outputs. Of course, each individual photon would only be registered in one, so I could never do this for a single photon. I would always have to do it for a series of photons. And in the end, I would find out something about the temporal coherence. So really, if I extend this here and I see my interference contrast decay, I will say that there is partial coherence in the system, which has to do with all kinds of indistinguishabilities or distinguishabilities. So what is coherence? It's the ability to interfere, and things can interfere if they are indistinguishable, which is basically what Feynman says, right? Feynman's rules. If things are amplitudes or paths are indistinguishable, we add the wave functions. Otherwise, we add the probabilities. All right, and this I would call longitudinal coherence. All right. So in these photon experiments, we also have to look at another kind of interference very frequently, which is named after their sort of first observers, called Hong-Ou-Mandel interference, because it was observed by Hong-Ou and Mandel in Rochester, and comes under the very under a title that you wouldn't expect, called measurement of sub-picosecond time intervals. And the story goes that this was very difficult to get past the referees, because the referees simply did not believe what was happening. And nowadays, this is a very important technique. I'll show you why in just a second. So what did they do here? They had a source that made pairs of photons in this crystal, and I'll show you later how this works. And then these two photons hit this beam splitter that we can translate. So we can either sort of have them hit at the same time or hit at somewhat different times. And it turns out if they hit at the same time, they will always exit the beam splitter in the same output. So they will both go here or both go there, which also means that the cases where you detect both of these photons in either detectors, each in either detector will be very small. So if we have the beam splitter in the middle, so to say, there will be no more of these so-called coincidences where we have one photon each. Yes? You need, if you had two, well, you need simultaneous photons. Simultaneous, yeah. If you have two single photon sources that produce two simultaneous photons, that would work just the same. They would not have to have sort of, well, they don't have a phase anyway, right? A single photon, if it's a Fock state, has no phase, in as much it doesn't really matter. And so why is this? Here we have the situation. This is our beam splitter, and we have two photons coming in one in either input mode. So every beam splitter always has two inputs, two outputs. And so there's three different outcomes. One where both photons go to the right, one where both photons go up, and one where one photon each goes in either output mode. And I'm saying this doesn't occur if these two photons are identical, indistinguishable. And why is that? It is because, again, we have two indistinguishable ways of accomplishing this. Either both photons are reflected, shown here, or both photons are transmitted, and we add the amplitudes. Now I've put a minus here, and that minus, I don't know if anybody knows where it comes from. It's not fermions, it's bosons. The minus in this diagram comes from the pardon me? Exactly, the sign of the reflection in the beam splitter. And in fact, it's a a mandatory sign that has to do with the unitarity of the beam splitter matrix. I didn't discuss that. We talked about the creation and annihilation operators before for the modes. If we go from one set of modes, the input modes, to another set of modes, the output modes here, we have a unitary matrix connecting the two. Otherwise, photons would be created out of thin air, right? This is why beam splitters, when they can be lossy, then they will have couplings to modes that we can't observe. But otherwise, optical elements that don't lose energy will have to preserve the energy, be unitary. All right, and so these two interfere away, so we never have this case in the ideal case. And why is this important for quantum communication? It is used for Bell state analysis. And this is what does the beam splitter testing here? It's actually two identical photons. If I write down a state of one or more photons, then they are bosons. So overall, their wave function has to be symmetric, right? What is this beam splitter probing? Which wave functions is it probing here? If it doesn't mind the polarization, it's really looking at the spatial wave function of these two photons. In fact, of course, if I write it down in terms of creation annihilation operators, then every wave function I can write down with those is automatically symmetric, right? By virtue of the, so if I write an A dagger and the B dagger applied to the vacuum, then this is a state of one photon in mode A and one photon in mode B with a completely symmetrized spatial wave function, which in this case is also just a product wave function. It becomes more complicated if I introduce other degrees of freedom, which I hope to do soon. And then if we have another degree of freedom, for example here, polarization degree of freedom, then of course the entire wave function has to be symmetric, which also means that if my polarization state for two photons here, in this case an entangled state, is symmetric, then the spatial state, where here are the two modes, written in a Dirac notation, so not with the creation annihilation operators, will also have to be symmetric. The other way around, if the polarization wave function, if we want that to be antisymmetric, then it's possible if also the spatial wave function is antisymmetric. And so, of course, the product of the two is, again, is a symmetric bosonic state, so that's fine. But now, if we have this state, which I cannot draw, hit the beam splitter, so again, my two photons, but now they're sort of entangled in their spatial wave function, this will turn, in fact, for this process here, this will give us a plus instead. And so instead of having the coincidences go away, suddenly we have a maximum. And in fact, these two terms would go away, but the calculation is not here. We could do that in the afternoon. We can use that to distinguish between this state and that state. Unfortunately, as you know, if I take two spin 1/2 particles and sort of look at the tensor product of their spin spaces, I get 4 states in total, right? And also, I usually divide this into a singlet and a triplet. Here is the singlet. Nothing's normalized here, but I hope you don't mind. And this is one of the triplet states. And of course, there's 2 more triplet states. We would, in the language of Bell states, we would call them a phi minus and a psi plus. And of course, all of these triplet states are symmetric under exchange, and likewise will their spatial wave function be symmetric. So if the beam splitter again doesn't mind the polarization at all, then that means that all the triplet states will show the dip, or will show this destructive interference for separate output ports, and only the psi minus will show constructive interference for separate output ports. So I have something that can distinguish between these two, but unfortunately it cannot distinguish between the various triplet states. With some added polarizers, we can do a little better, but it's proven that we can actually not do perfect ever. To do perfect, we would really need a 2-qubit gate. Yes? Yeah, that's actually a bit of a funny way of writing it, and you know, this is kind of an HV minus VH. That's type. Oh yes, right. Sorry, that's 0. No, that's wrong. Yeah, that should be a VH. Thanks. Didn't even see that. All right. So I was talking about what we could do with optical qubits. Yeah. Wow, there's even milliseconds here. Didn't know you were so accurate in India. And then there's milliseconds. There's milliseconds, yes. It's hard to read them because they're so fast, but okay. So I was going to talk next a bit about how to encode quantum information into photons. Many of you will have seen the polarization. That's not all. In fact, if you open the Knil-Laflamme-Milburn paper, you will find that an optical qubit is represented by a so-called dual rail qubit, and theoreticians simply draw 2 lines, and so if the photon is in the one state, I guess I should call it in one of the 2 modes, mode 1, then it might be a 0, and if it's in the other mode, it's a 1. All right. In real life, things are not so easy because there's no rails for photons. If they propagate in free space, in fact, they would diffract. So if you could send them through a lens, and at some point you could catch it again in a lens. And this is a picture from a thesis that from a PhD thesis of one of my fellow students in the 1990s, who in fact implemented such a thing for 2 entangled dual rail photons. What was the tricky thing is here, you want to preserve the phase of the 2 photons as they propagate. But as you know, the optical phase, the wavelength is about a micron. So if any component moves by a fraction of a micron, the phase will also change dramatically. So this is not usually a very convenient way of encoding the information, because it will really be phased by every movement, every vibration that your mirror makes or your lens will dephase this. And so it took him a long time to get this stable, but in the end it worked. So the other thing is that eventually when you build an interferometer, when you want to compare different qubits, this becomes a bit cumbersome. Yes? Sure. Please. Right. Yes. Yeah. When you get a, oh yeah, you mean it's reversed? Yes. Right. In fact, the Gaussian, we're talking about in this picture. I'm thinking of a single Gaussian beam. I don't know if you've ever looked into Gaussian beam optics at all. So you wouldn't actually consider imaging because a single mode cannot encode an image. A single mode cannot encode an image. An image has a lot of information, right? Every point source in your image is one source point, and you want to image that to a different plane, and you get an inverted image. But here I'm talking about a single Gaussian mode, something that might come out of a laser, and that in itself would not have an image. I mean, the entire wavefront here is one coherent wavefront. I think that might be another good discussion for tutorial, because it's going to take a little while. So this is really just one wavefront, and if it will converge, in fact, it will be planar in the center and it will diverge again. whether you want to see this thing as inverting or not. But there's nothing here to cross. It's a single wave. It's a single wave front. Whereas in the image, you really, I mean, the rays that you construct in an image, they emanate from different point sources in the object plane, right? And every one of those, in fact, does exactly what I do here, but with only one of these Gaussian beams, you cannot construct the image. This actually corresponds to a. Now, let's discuss that in the afternoon. That's a really nice optics discussion, but it's going to take us a bit, I think. All right. As I said, the phase between two of these beams, the relative phase, would be really hard to preserve. So let's do a trick. If we wanted to send these two beams a long distance and rather not lose that phase, we'll just put it all into one mode, okay? And the way to imagine is, now imagine that this is our rail 1 and our rail 2 are just two arms of an interferometer of which we want to preserve the phase. Now let's this is supposed to be signifying a long distance in this interferometer, and here we want to have a stable interference between the two arms. So now imagine we just cut this here, take this part and put another beam splitter here to put it in the same mode. Now we send it through our long distance or harsh environment, and here at the back we kind of demultiplex again, and we complete the interferometer. Looks very simple, but of course I've neglected something. I've neglected that there is a second output here, right? And also that there is a second input here, potentially. All right, but we'll look at this. This is called so-called time bin qubit. So no matter how we made it, so this is how we could possibly sort of think about making these. But we can we don't have to argue here. We can encode our photon into, before we encoded it into either of two beams. And these are two different spatial modes. And I'm saying we can just as well encode our photon into either of two temporal modes. Okay? So this is supposed to be pulses that, say, propagate in space, and then of course in time they're time is the other way around in this by the velocity of light. So we could encode our photon by either being in the early pulse or in the late pulse. All right? I mean, there's I'm saying here that they are quasi-orthogonal because if they are in real life with finite spectrum, I can't really have perfectly orthogonal modes that are localized perfectly in time. That's not so important. So here our state would be a superposition of this early and late pulse. And why is this interesting? Because if I send this pair of pulses through an optical fiber, then the relative phase between the two, they will see the exact same stretch of fiber. Anything that happens slowly doesn't matter because they'll see the same thing. If something happens extremely fast, namely between these two pulses, then it would be bad, right? Then the phase between this E and L state would be modified. Now, in real life, these would be a few nanoseconds apart, meaning that anything that happens to the fiber would have to happen on this time scale of nanoseconds, or in frequency terms, it would happen at gigahertz frequencies. Mechanical things usually don't happen at gigahertz frequencies, at least no large things happen at those frequencies. And so this is something that sort of has for long distance propagation has a built-in decoherence protection. Would use the same spatial mode no matter whether it's in free space or in a fiber. Would really only use two temporal modes. And this is in fact what all modern QKD systems that you can actually buy from 2 or 3 companies. You can buy quantum key distribution systems. They all use some variant of this encoding. Here we go. Very good question. So how do we, now we want, imagine we've prepared this. How do we analyze it? Okay, so we need this delay interferometer here that splits our beam, and now it produces 2 copies here, 2 copies of the early and 2 copies of the late, and it interferes the late copy of the, sorry, this is the late copy of the early pulse and the early copy of the late pulse. They meet here at this beam splitter, and at the output of both outputs of the interferometer, we get 3 possible pulses. So it's even worse. We lose even more in the worst case. And these 2 center ones are really the superpositions, and there's the sort of in-phase and out-of-phase outputs. So, and this is what you would expect, right? In any interferometer, I have 2 outputs, and so here I have E plus L, or minus E plus L with the phase that I put in here, and here I have E plus L, the 2 orthogonal outputs of the interferometer with this phase. And now, this is a very good point. We lose a lot here. This is, however, I would argue a technical problem, not a fundamental problem. I'll get to you in a second, right? If I could imagine having a switch here, and I could direct all of the early pulse the long route and let the late pulse pass entirely, in which case I would only have these central peaks, the output, the central pulses. Also, another thing I should add, if I actually wanted, you see here with a 50-50 beam split that the output, I only get equal amplitude superpositions. I cannot go for an arbitrary state on the Bloch sphere, right? Or Poincare sphere. If I wanted an arbitrary state with some amplitude E and some amplitude L, I would have to change the reflectivity here, in which case then I would get the 2 orthogonal outputs at some kind of antipoles of the Bloch sphere. There was another question there. Right, but if every one of your photons is really important to you, because I don't know, you've done an experiment, it cost you a lot of effort, you don't want to lose that photon. And in fact, if you now do this for a multi-photon state, then it would scale really badly. For every photon you add the loss again. So in that sense, I agree. It would always be better to avoid them. For doing any demonstrations, it doesn't matter. And for QKD, quantum key distribution, it also usually doesn't matter because there's much bigger losses elsewhere than here. But in general, in fact, there's one demonstration has been done where this was a switch. The problem is that real life switches are also not so great. So they usually add more loss than they gain here. Yeah, that's an interesting. All right. So now one more thing. I want to say a little bit about how we get photons to far away places. You've heard about the Chinese, Beijing, Shanghai QKD link, which will actually consist of many, how many? 32, I understand, sublinks, right? So these will be single mode optical fibers, and I'll say something more about that. Another option might be to have photons broadcast from a satellite. Thomas Jennewein is in Waterloo is working on that, and also, of course, Wei Pan. In fact, what most people favor now is to send the photons up to the satellite because it seems to be very difficult to get the sources on board. Although the Chinese have supposedly managed, we haven't seen results yet. But we'll see that. So optical fibers, I guess you all know that light bounces by total internal reflection in this fiber, and if I make it small enough, it really doesn't bounce anymore. It just stays confined in this. There's a lot of stuff happening to photons when they go through fiber. Polarization is usually not maintained because the fiber is spuriously birefringent, so it has small birefringent, meaning that the two polarizations propagate at different speeds. That by itself wouldn't be a problem, but then the fiber also does twists and turns, and eventually, you know, from time to time, the axes change, and so you have two things. You have usually you have some kind of main component of the birefringence, so that what you send in is H and B, or you will get two output pulses. But also for long fibers, there's some kind of diffusion, because these the axis of the birefringence vary along the fiber, and so we have a spread that goes as the square root of L, which is actual depolarization that you cannot undo by any shifting. All right. Another thing is, and I mentioned this before, which wavelengths do we like to work at? We like to work at 1.55 micron or 1,550 nanometers, because this is the place where we get the lowest loss. And this is actually an interesting story. I don't know if you heard that in the 70s, the Japanese telecom company had a test bed, a microwave link with hollow waveguides, which was a few kilometers long and cost a fortune to build. And then the first optical fibers came out with a loss of 20 dB per kilometer, and instantaneously this microwave link project was scrapped. So even at 20 dB per kilometer, it was clear that the microwaves would never compete with light waves in this regime. And so by a lot of engineering, this has been reduced, but you can also see the main component here is Rayleigh scattering at the actual material, which is silica, fused silica. So at that point, we cannot hope to actually be better ever than maybe 0.1 dB per kilometer. But mind you, that's a really low loss, right? 0.1 dB means about 97% transmission, if I have this correct in my head. 97%. So you're looking through a block of glass that is 1 kilometer thick. If you ever looked at a window pane from the side, you actually, it looks dark green, right? And it's dark green because it swallows all the light, really. And it's just 1 meter of glass. A regular 1 meter window glass block is almost opaque. So it's quite amazing. So this is how far we can go, and you also know that for quantum key distribution, this means that after about 100 kilometers or a bit more maybe, all photons will be, most of the photons will be lost, and we'll compare with noise at the end. All right. You see, there's maybe one more thing to say about free space beams and satellites. Quite interesting, actually, because if we only had diffraction, so if we send, you know that we send out a beam, a laser beam. If I point it here somewhere, it's a small spot. If I point it there, it's a large spot, which is exactly what we saw before, right? It diffracts out. But I start with a small beam, and then I will get a large beam. But this spread actually goes as the square of the distance, so it's not exponential. So you could think that maybe there is a way to overcome the exponential loss with distance. Unfortunately, there's other components that make this worse, turbulence in the air. And there's another component that is exponential, and that is scattering. So as long as you go through air, there will be scattering. And so eventually, also the free space channel will have an exponential loss. It doesn't matter that this is quadratic. I'm saying quadratic because if we have a finite receiver aperture, then I guess we get something that scales as a square. All right. So yeah, something about satellites, but I don't know. Maybe this goes a bit far. Just saying that if you have a satellite that you want to broadcast the photons from or to, if it's a low satellite, it actually moves fast, and if it's far away, it's really far away. And if it's geostationary, it's 36,000 kilometers away. And so optical communication to geostationary satellites is really, really hard. So all the current projects concentrate on low Earth orbit satellites, a few hundred kilometers up. So that is nice. It's not so far away. You can actually catch some of the beam, but you only see it for a couple of minutes. And when you see it just above the horizon, it's really difficult to get any photons to and from it. So quantum communication on that scale is going to be hard. Yes? Yes. If you look at this picture, exactly what happens here. The point is right, but what's the problem? Can anyone see what the problem is? In fact, I think that wouldn't be much different, the point being. Mm-hmm. Right? Right, but neither is a, so assuming that the satellite aperture telescope will always be small in some way, right? I mean, what I would say is that it really doesn't matter, because the aperture that you actually have is always really small. So if I take a 1 meter telescope, then the best I can do is go out parallel, because whenever I go through a focus somewhere, it's going to be an effectively smaller aperture. It's not going to change my K distribution, and in a long distance, the K distribution is all that matters. So you could be better if you had a huge telescope. I mean, by huge, I mean really huge, not just 10 meters, 100 meters. Then yes, because then you're maybe 100 kilometers away. Then your telescope aperture is still 1,000 times smaller than that distance. So then you could focus and gain a little bit, but not at this sort of regular arrangement where you have maybe 1 meter or a few meters and you're a few hundred kilometers away. Then it really doesn't matter. You could, whether you start with a plane or if you have in fact, if you have a slightly converging, I think it's worse, but I don't know for sure. Yes. I think that, yes? Well, so there's two things. It's a single mode, if you go through a telescope perfectly. But there's another thing that's going to kill all these fine arguments, and that is the turbulence. The turbulence in the air, especially near the ground, is so bad that all of these arguments focusing go to waste anyways. Okay? So effectively, if you want to know in more detail, I can tell you. But the fluctuations in the air, at least in the lower troposphere, mean that your effective aperture is always about the size of 10 centimeters. So this is the size over which a wavefront can stay roughly coherent in the lower troposphere. And in that sense, it doesn't really matter. But I think about the argument, if you go from the satellite down, it could matter if you had a large enough telescope. I think then you might have a point. All right. Oh, almost done. All right. It's by far not as far as I wanted to go, but we'll see. Change for a second. I was going to talk a bit more about the components, the beam splitters, but I guess I heard you already know. So this is what I meant before when we go from one set of modes to another set of modes. We have a unitary matrix connecting these, and this is in fact here I have the sign somewhere, the minus sign that we talked about in the beam splitter. Yeah, this is just if the beam splitter is the simplest case is 50-50. We get, this is sort of our preferred version, which is pretty much the same matrix as the Hadamard matrix, except in optics we usually prefer this version where we have the phase distributed so that we have an I in the the off-diagonal elements, and not the -1 in the bottom right. Yeah, that's the other one. Okay, and then some time ago, and again, actually now with these ideas of boson sampling, people are interested in multiport beam splitters. If we add more input and output modes, always the same number, of course, then we get to sort of the symmetric 3-port or 6-port device, depending on your preference. Some people count inputs and outputs. Other people only call inputs, because the output is going to be the same number anyway. And this would be the matrix of a symmetric 3-port. And it's not an accident that it also looks like the discrete Fourier transform in 3 dimensions. It's really the same thing, which is nice. And a former colleague of mine in Innsbruck proved that any one of these multiports can actually be built from just beam splitters. And that is nice, by decomposing the entire unitary into sort of 2x2 product of 2x2 matrices. And then yeah, same in 4x4. So yeah, I don't know how we want to do. I have a lot more time in the afternoon, I think, right? So let me just see. Yeah, maybe I'll just okay. I'll say something about polarization still, because many things are done with polarization, and maybe not everyone, I don't know, it depends on your experience, is so familiar with that. I mean, we usually learn in quantum mechanics, we do with spin half particles, and then when we deal with photons, we again have an effective spin half particle, except it's a spin 1 particle that has 2 polarization states only, because we have no spin 0 component. And so we end up with polarizations that are sort of represented in real space as vectors with 2 arrows, because up and down is the same thing, right? So our orthogonal states are horizontal and vertical, or plus and minus 45 degrees, or right and left circular, where the convention is that right circular means that if you look into the beam's coming at you, you see the electric field vector turning clockwise. All right. An important device is a polarizer. That's why polarization is so convenient, because we have actually something that works really well as a projector to very good degree. For example, a thin film polarizer, or we can assemble something from birefringent material that will let only one polarization pass. With the, I guess, record devices have about a 10 to the 7 extinction ratio. So we can only, for every 10 to the 7 H photons, we get 1 V photon through. And in fact, these birefringent devices can be arranged so that we get both outputs of this operation, so we can get the H through and the V reflected. And that's very convenient. And in fact, if we write down the matrix of all the input and output modes here, so we have, in this case, we have 2 input modes that are both on the left side, and then 4 output modes. Of course, there's also 4 input modes in total that I'm not showing here. And if you write this all down, the matrix looks like the matrix of the C0 gate. And it is, in a way, but it's a C0 between polarization and space. So it's a kind of hybrid quantum gate. Sure? Yes, annihilation or creation doesn't matter. Creation operators, right. It doesn't really matter. It doesn't really matter. Of course, the matrix would be a conjugate matrix, but in the end, it doesn't matter. You can do the, I mean, we only map the modes to some other modes. Any unitary matrix is allowed. The question is what we actually have in the lab. But if I have a state given, then usually the state is sort of creation operators applied to the vacuum. So then I would use the matrix that applies to the creation operator. But then, in any case, whenever I do a measurement, I always have sort of the absolute square, and so both of them will eventually, you know, in the photo detection, I have the E minus and E plus, so I always have the annihilation and creation operators, both in the final probability. In fact, I'm trying to think, matrix even the same. Anyway, for this matrix, it wouldn't matter at all, right? Because it's all real. Yeah. Well, in this case, we're yeah, of course, it would be the, I guess, the complex conjugate matrix. Because we're talking about connecting different modes. We're not talking about sort of transforming from annihilation to creation operators, which wouldn't be a unitary anyway. Okay, but maybe we should stop here, and then there's some more about polarization components, but it's not so important for now. And something about detectors also not so important. And then in the afternoon, I'll talk about pair sources. All right.
Any more questions?
Or over lunch.
Okay, let's thank the speaker.